pleasure to have Ludovic Tangpi from Princeton University. So Ludovic got his PhD in 2015 at the Humboldt University in Berlin and Constance, under the direction of Michael Cooper and Mette Sohner. And then he was a research assistant at University of Constance. Then he becomes a postdoc at Vienna, University of Vienna, with Walter Schachammeyer, whom everybody knows very well in financial mathematics. And since 2018, he is an assistant prof at Orphy at Princeton University. And it's our great pleasure to hear about games in the weak formulation and their mean field game limits. Ludo, the screen is yours.
Thank you.
Yeah,
Thank you.
People are still saying the floor is yours. I don't understand why. The screen is yours.
There's no floor. Yeah, the screen is mine, and I am using it. Thank you for the introduction. Yeah, I really appreciate the opportunity to present this work here, and I sincerely thank you for inviting me. So I'm going to talk about large population games and their link to mean field games. And I mean, this is something that I've tried to do in the past 2 years, and the idea is really to provide or to explore stochastic analysis approach to studying the mean field limit in application games. So the work is based on materials from the work with excellent memory, and it's a work in progress. So I would really appreciate any questions or comments or criticism from the work, because then we can try to improve it before finishing it. So since this audience, I mean, since many people here are experts in mean field games, I will not spend time motivating the work or the results, or jump right into the setting and then start talking about the approach and the results. So the setting, I mean, in general, we are considering a large population games that takes a following form. So here we are dealing with a continuous time diffusion model where a given agent, called it agent I, is trying to control a given diffusion. Here we have a sequence of Brownian motions W. They're all independent. We have some diffusion coefficient, but the important guy is this one here that the agent is trying to control. So it's trying to control the drift of this diffusion that allows to know how much, I mean, by changing alpha, which is the control process, player I or agent I is changing the drift of the diffusion of the position X in a given direction. So interesting here is this quantity here. This is the interaction quantity. So we assume that there are n players in this game, and they are interacting through their positions X. So X here is a vector containing n positions for each of the players. They're also interacting through this guy here, which is the control. I mean, this is a vector on all of the controls of the players. So this guy here is alpha 1, alpha I minus 1, alpha I plus 1, alpha n. So this vector contains all of the strategies. And this game is interesting in that the position of this player is impacted by the average position of all of the players, but also by the average action of all of the players. Now, to specify these dynamics, what the player I is doing is trying to optimize this reward function. This is given by some running reward F and some terminal reward G. And again, these things are depend on both action and the position of the player, as well as the average of what people do in the system. So this is a typical large population game, at least in the continuous time framework, where agent I is trying to optimize this quantity. And of course, because this optimization problem in n dimensions is extremely hard, we usually settle for a Nash equilibrium. So we want to find some strategy, some vector strategies such that one player does not have an incentive to deviate. So if one player deviates from that vector, he or she is not going to be better off. So this is the Nash equilibrium that we're interested in general. And in this large population setting, so N here is assumed to be large, things become quite messy. And for many reasons that you guys know well, it makes sense to consider the mean field gain formulation of the problem, right? It makes sense to consider this mean field gain formulation because it has so many advantages. So in this talk, what we want to do is to study or discuss a rigorous way of linking this final population game to the mean field game, rigorously showing that there is some convergence and discussing which sense we have the convergence between the finite n population game that is that we play in practice and the limiting mean field game that is used in for analysis. Well, of course, this question is interesting for many reasons. First of all, at the probabilistic level, it's interesting because it is somehow another level of abstraction on top of the usual interacting particle limits that has been studied for many decades. Here, on top of the interacting particle system that we have here, we also have a control that comes on top of it. And it's interesting to know whether this powerful particle system theory generalizes to the case where we have controls. But also because the mean field games is extremely, it's an extremely powerful theory that has have so many applications in the past decade. And it's interesting to know whether these mean field games really, to which extent, in which generality it comes from the finite player game, that again is the one that is played in practice. So the pioneering work on the understanding of the link between the two games are probably those by Dan Lacker and Marcus Fisher, where they show that when you are able to plunge this controls alpha in the set of probability measures, so consider the so-called relaxed control, then one is able to use the comparative properties of set of probability measures to derive accumulation points, namely to show that a sequence of Nash equilibria accumulates an accumulation point, and this accumulation point has to be a mean field equilibrium or the solution of the mean field game. More recently, there's been an approach based on PDE reformulation of the problem by these people here. The approach there was to start by the HDB characterization of the n-player game and show that this PDE written on an n-dimensional space converges to the so-called master equation that characterizes the mean field game. Of course, under proper existence or well-postness of the master equation and under enough regularity on the solutions. So last year with Mathieu Laurier, we also took up this this problem, and we looked at it through stochastic analysis formulation. So we introduced a so-called backward propagation of chaos argument. That is just propagation of chaos, but for a particular system that evolves backwards in time. And we show that having this kind of propagation of chaos allows also to obtain to prove the link between the n-player game and the mean field game. I mean, all these works or approaches, the work for Markovian problems and the way the control problem is specified can differ from one case to the other. Perhaps I should mention that in this case here, they consider feedback controls, where we consider in this paper with Mathieu, we considered open loop controls. But the common feature in these games, I mean, these two cases is that they do not allow interaction through the controls, and they are working the Markovian setting where the reward functions and the drift functions depend on the position at the given time of the player, I mean of the player at time t. So the motivation underlying the work that I'm going to present here is the following. So consider this simple example that comes from finance, where one wants to hedge a position on a given option. For instance, let's say the option is given by G, and you're investing in a market where there's price impact that's given by this quantity here. I mean, this is the average trading speed of all of the players, of all the trades in the market, and there's transaction cost in the market. Then after some computations, one shows that the problem solved by each player is the following one here. Now, here, this is a game because due to the price impact, the value of the player I depends on the average value or the average controls of all of the players in the market. And in this case, I mean, this example that I have here is hedging of a path-dependent option. So the value at the terminal time does not depend only on the position time capital T of the player I, but on the whole history of that player. So because of this formulation already, what we did with Mathieu would not work anymore, because this function here is a function that is defined on an infinite dimensional space, not an Euclidean space, like what we did in that paper. Another example, I mean, that comes from the same, I mean, the same model where let's say you have some delay in the response in the system. So in such case, we have delayed, time-delayed games, where an example, for instance, would be where the terminal cost here, the terminal reward here, sorry, depends on T, but up to a given delay delta. So delta here is a strictly positive number. So in this case, again, we have in a typical non-Markovian situation, and it will be interesting to know whether such games will again converge in a large population limit to a so-called mean field games, and therefore extend the results that I cited in this for this paper here. I mean, I just wanted to make the point that this kind of non-Markovian settings here with the running supremum or the delayed are not just purely theoretical considerations. There are interesting cases like in works by people in the audience where they have models on the in finance, I mean, the systemic risk models where there is a delay response in the problem. Of course, in this paper here, the delay is on the control, not on the state. The control delayed case is much more difficult to deal with. I mean, as far as the limit is concerned, in this paper, we are looking at only delayed or non-Markovian settings on the state processes. But of course, if you are considering feedback controls, then a delayed control can be seen somehow as a delayed state, right? And you can write something of this form here, and you're back to the delay state, and hopefully you can see something. But we are going to consider just a delay in the state process, at least dependence in the history of the state process. Good. So, like again, the common feature is that we are in a non-Markovian situation, and you want to be able to extend the results of the above papers, especially the one that I did with Mathieu, to the present non-Markovian situation. Good. So to do that, we are going to introduce a slightly, I mean, a different formation of the game. Above here, in introduction, it was the strong formulation of the game where we're controlling the state process. I mean, changing the control will change the position of the particle X. Here we're going to consider the game. We're going to reformulate it slightly, and we're going to control rather the law of the law of the state process. So here, the probability basics omega fp is fixed. We assume this probability space carries a sequence of independent Brownian motions, and for each I, we let X be the strong solution of this uncontrolled STE here. So there's no control here, and X is the strong solution of this STE. Now we consider the law of this process. So by changing the drift of the process, we have different controls, and therefore we are trying to optimize over this law of the control, or this law of the state. Sorry, and otherwise the reward dynamics. We have a function X, running reward, and the whole degree of the of X. It is on the average position of all of the systems and the average actions of all the systems. And we also have a terminal reward depending on the position and the average position of all the systems. The interesting thing here is just that X is not controlled anymore. What we care about is the law of X. And this is the weak formulation because with this definition here, X is exactly a weak solution of this controlled STE because S satisfies XTE under the probability measure P alpha. Can you see my screen? I think something happened here.
Yeah, it seems that the connection is not really good. What's going on?
Because it seems like, okay, I will unshare and share again.
Yeah, go.
At some point I couldn't. Let me show. Somehow it's not working. I don't know why.
No.
Let me share. Try again.
Moyuki, do you think it's best maybe to relog on Zoom, restart Zoom for him on his side? Here we go. That's what he's doing. You're back? Are you back, Ludo?
I'm back.
Yeah, so now you can start sharing again.
Do you hear me?
Yeah, we hear you. We see you.
It's not working still. Come on.
That doesn't work?
No, I'm trying to share again, but it doesn't work.
Do you want to send your PDF to Tomoyuki?
I think it's working now.
Okay,
Is
good.
it working now?
Yeah, it's good.
Okay.
Good.
Okay. If it doesn't push, I mean, let's try. I hope it goes now. Okay, let's continue. Sorry about that. Yes. I don't know what happened. So where was I? Yeah, I was. I think it was here. I was explaining that here we have. So this is the weak formulation because here the controlled process X is a weak solution of the STE that we care about. I mean, of course, there's a sigma here, but I can just put sigma -1 here to come back to what I want exactly, but it's not so important. Good. So in this setting, I mean, this is the n player game. What would the mean field game corresponding to this setting be? So the mean field game takes exactly the same form as the n player game. I mean, the usual form. The difference is again that state process is uncontrolled, and we care about its law here for this probability measure. And it's defined as usual. So we fix some flow of measure psi. I mean, this is a flow of measure that depends on the state and the control. Let's dimension R1. And then we solve this standard control problem here in a weak formulation. And we find the optimal solution that we call alpha hat. This is the optimal solution. Then the second step, as usual, is the fixed point condition or the consistency condition that is given here. So we would like to find the measure, find the control alpha whose law coincides with the law that gives rise to it. The only difference here is that in the usual mean field game formulation, the law P here is the physical law, but here you take the law of the optimal control in this weak formulation. Good. So these are the two games that we're considering, and again in this case we allow dependence into the whole path of the state. And perhaps let me go one step back and say something about the information structure here. I think I skipped that part. So here, of course, this X is adapted to the filtration given by WI only. I mean, this is by design. The important thing is alpha. So here, alpha is the control of player I, and we assume it to be, sorry about that. So alpha is progressive with respect to the filtration given by the first n Brownian motion. So n Brownian motion, because you have the n player game, we assume that they have this idiosyncratic noise W1, Wn that brings a noise or the randomness into the system. And each player observe all of these Brownian motions here. But in the mean field game, alpha is progressive with respect to the filtration given by this W only. I mean, let's say it's W1. So it's given by this W1 only. And the idea is that in the limit, we believe that all information will collapse to just one Brownian motion for just one player.
Can I ask a quick question? So sure. With the n-player game, you mean that you are looking at the open loop?
Yes, we're looking at the.
That's what you mean. Okay.
Yeah, so we're looking at the open loop setting, and I'm going to come back to that at the end of the talk.
Okay. Thank you.
Good. Good. So just quickly, the main assumption that we make in this model. So we assume that the drift and the terminal reward are Lipschitz continuous functions, and we'll also introduce the so-called Hamiltonian or reduced Hamiltonian of the system that is also going to be Lipschitz continuous. And we assume B is bounded. So maybe the take-home message is that we would like to have enough regularity on the reduced Hamiltonian and these coefficients of the problem. I believe that if you replace Lipschitz by locally Lipschitz with more work, you will probably end up with similar results. Now, so this is an assumption and very natural. The assumption is perhaps a bit new here, or maybe less natural, is the following. So we assume that this reduced Hamiltonian has a maximizer. I mean, so far this is also a natural assumption because this maximizer depends on X, the law, and Z. So what we say is that, there's a typo here. This function should depend, of course, on A, the control, and this should depend on the control A. So I forgot that, and I'm optimizing over A. So A here is just to mean alpha. This is the control. But the important thing here is that the psi that is here should be understood as what? I mean, as a candidate for the law of X and alpha, right? Sorry about that. And one here, so psi, one here is the first marginal of this law. So what I'm saying is that when I optimize this reduced Hamiltonian, it does not depend on the second marginal or the law of alpha. It depends only on the law of X. So this is what this assumption says. And this will not, of course, not be satisfied in full generality, but the idea is that we do not want this optimal value, which in the end would be the mean field equilibrium, to depend on itself. So we want to have an explicit factorization of the mean field equilibrium, not an implicit one. And this kind of condition would hold when B can be decomposed in a nice way. For instance, this B corresponds to a function that depends on X, on A, on the law of X, and another function that depends on X, on the law of X, A, alpha. You see that when I optimize, with similar decomposition for F, you see that when I try to maximize this function, this part will not fully be relevant, and only this part will be relevant. And in this case, you see that it depends only on X and the law of X. Good. So these are the main assumptions that we make. And with these assumptions, we have the first result of the talk, which is the existence or the well-posedness of this mean field game in the weak formulation. So the result says, well, if this quantity here, so this quantity here, LG is the Lipschitz constant of G, the thermal reward, LB is the Lipschitz constant of B, the drift, and T is the horizon. If this quantity is small enough, then we have at least one mean field equilibrium in this weak formulation. And if this lambda that maximizes the Hamiltonian is unique, then we have a unique mean field equilibrium. Good. So both existence and meanings here are not completely new, because in this work by René and Dan, who introduced weak mean field game in weak formulation, they also derived existence uniqueness. The thing that in this work, they went through the approach of first solving this problem here and then defining this map, and sure this map admits at least one fixed point. And the novelty of this theorem is mostly the approach that we use, not really the result. The approach is novel because we obtain existence here by solving this what we call generalized Markin-Vlasov equation. So here is the technique. We show that if this equation, this is a backward STE, if this equation has a solution, then putting alpha hat like this, again, lambda is the maximizer of the Hamiltonian, then this one here is the is a mean field equilibrium. But we didn't really do anything that is, it's not like it's much faster than this one, because this equation here has some subtleties. First of all, observe that it is not a constant drift, because this alpha hat depends on Z. So this is really nonlinear in the control process Z. But most importantly, it depends on the law of Z. So this L here means the law of Z with respect to, so L alpha hat of Z is the law of Z with respect to the probability measure P hat. So it depends on the law of Z. So this is the Markin-Vlasov equation. And on top of that, the equation, the probability measure itself is unknown because it depends on alpha again, which we didn't know. So in some sense, the fixed point condition that is written here is embedded into the equation itself here. Because again, if I remove this part here, I put some abstract probability measure Xi, I remove this part here, I put some probability measure Xi, then everything abscesses to a standard Markin-Vlasov equation. And what I'm doing here is just to impose the fixed point condition by having this thing here. And this gives us this equation where the probability measure itself is an unknown. Then, I mean, solving this equation allows now to obtain the mean field equilibrium. And the things that the characterization goes.
Can I ask a quick question? I mean,
sure.
Take the liberty to ask you a question in the middle. You don't mind, right?
I don't mind.
Okay.
I appreciate it.
Is that okay? Because I will forget anyway at the end. So this is a non-standard formulation. I mean, it's a little bit new compared to what we used to see. Can you comment on where do we see on this formulation that you are doing a mean field game and not a mean field control problem? Where do I know that this is mean field game? Because it's a little bit confusing here.
Yeah, okay. Here the game happens, I mean, it's because of this quantity here. So if I had a control problem, I would not have this quantity here. I would have just some law called psi, for instance. And I say, well, at the optimal control, I would like this to be satisfied. So I just replace this arbitrary control psi by this quantity here, which is that I put here, that I put there. So this is where the mean field game occurs. If I was doing mean field control, I think probably difference yeah, I wouldn't have this fixed point condition here. So here it would be just the law of the law of Z, I guess. I mean, the short answer is that the mean field game occurs here and here.
Thank you. Thank you.
Sure. Yeah. So I was saying that this characterization goes both ways in that. So here I was saying that if we solve this equation, that we get a mean field equilibrium, but also if I have a mean field equilibrium, then this equation has to have a solution. That's how we get uniqueness in this case here. Of course, this needs that lambda be unique. Now, maybe to compare again to the work of René and Dan, there they obtained uniqueness using Lasry and Leon monotonicity condition. Here obtained uniqueness using, thanks to this smallest condition. But this is it's not really surprising because without that, we know that there are counterexamples for uniqueness. So now I come to the last method, which is the mean field limit. And the idea would be to use, this equation here is going to be very important for the mean field limit. And the idea is follows a very similar idea of what we did with Mathieu, namely to try and obtain this mean field limit by the so-called backward propagation of chaos, or the propagation of chaos for a particle system that involves backwards in time. So this is exactly the same as the standard propagation of chaos for interesting particle systems. The caveat here is that the probability measure for the limiting system, or with respect to which we take the limits, is going to be this P alpha hat, which is the probability measure, the law of the optimal of the mean field equilibrium, which is, just to recall it, it is written here, where I plug here, alpha hat is the optimal value, and psi is the law of the optimal value. So to summarize what I was saying, the approach to get the limit follows the following four-step approach. In the first step, we find a nice particle system characterization of the mean field game and the mean field and the end player game. So for this one, I've already done it. This was this generalized marking class of equation. for the n-player game, I'm going to do it on the next slide. After doing so, one proves the characterization of the equilibrium themselves using this particular system, and in the third step to prove convergence of this system to that one, and in the last step you identify the limits. So it's really algorithmic. Good. So the first two steps are the following. Using the weak formulation of the game, one can write down the Bellman, the dynamic programming principle, and use Bellman optimality condition to obtain this backward STE here. Notice is pretty standard. You first start by writing the DPP, and then you write down the Martingale optimality principle. You say, well, this strategy, as for every strategy, say this process is going to be a super martingale, which is a martingale for optimal control, and you use Dupmer decomposition to derive the drift, which is the generator here. So this gives us this system of equations, which are all coupled. Again, the alpha hat here is the system of the equilibria, and this Ln here is the empirical measure of X and the system of equilibrium. So you see that this system interacts through the empirical measure of CII. This is the diagonal of the control processes. It appears in this empirical measure. Otherwise, in this case here, this one is just the value CII, but this value here is the diagonal of all the controls of all of the players. We have the sum over all of the controls here because of the information structure. We say that our players, they look at all of the Brownian motions, W1, Wn. That's why we incorporate all of the Brownian motions here. Otherwise, everything else is understood. And the H, of course, is the Hamiltonian that I defined at the beginning, which I assume to be Lipschitz just in order for me to take the limit here. And yeah, and the value function of the player I is given by the initial value of this equation. So good. So now the second step, which is the convergence of the two equations, is given here. We are going to assume in addition that, so this lambda n characterizes the n player game. And we assume that if this lambda n converges to lambda that I had before, I mean, we give conditions in the paper under which this assumption, this convergence holds, but let's say we can, this function lambda n that characterizes the n player game or the Nash equilibrium of the n player game converges to some lambda which maximizes the Hamiltonian, let's say at a given rate, for instance, in L2, then we have the following. Then the y, the value process of the n player game, converges to the value y of the generalized Markin-Vlasov STA, and same thing for the controls in the H2 sense. So the diagonal values of the controls converge to the control of the generalized Markin-Vlasov STA. And here I'm just writing this one because in the paper we're able to find precisely the rate at which this convergence occurs. And this rate depends on the speed of convergence of the empirical measure of this IID guys here, the positions to the law of the position. But it's not so important. The important thing is that this converges to 0. Now, the last step now is to bring everything together. We have, remember, we had that alpha was a function of z, and we have here that alpha n, which is the Nash equilibrium, is a function of xi and zi. So we know that this one converges to x, this converges to z, and this converges to the law of x. So putting all this together, we have the result, namely that the Nash equilibrium of the n-player game converges to the mean field equilibrium at a given rate. And same thing, the value, or let's call it the value function at equilibrium, converges to the value of the mean field game. So this is precisely the sense in which we meant that we link the mean field game and the mean field equilibrium, or the sense in which we have the convergence here. So it's really that if we have a Nash equilibrium, then this process converges to a mean field equilibrium, and the values of the game or the two games converge. Cool. So this is the main result, and the proof is first the argument that I described above. We first start by analyzing the n-player game and the mean field game, and we show the limit in the abstract sense, and then we show the limit for this one here. So I think I'm out of time, so I will perhaps jump the discussion here and talk about the closed loop versus open loop formulation. I'm going to go fast here just to say that in this setting here where we have weak formulation of the problem, the closed loop and the open loop Nash equilibria turn out to be the same, because when a player changes the control alpha, it does not change the value of the state. So that if the filtrations of X coincide with the filtration of W's, then any closed loop controls like this one would also be an open loop control, and we're able to get the limit also for closed loop controls. So I will stop here, and thank you for your attention.